Hello, in this lecture we'll find out the length of line segment X. In the drawing we have two quarter circles. The two quarter circles touch each other at point B. In addition, we know that line segment AB equals to 1 unit in its length. We also know that line segment QS equals to line segment SP, and our mission is to find out the length of this line segment BC is equal to X. Okay, so first of all, because of the fact that this is a quarter circle, it means that AB and AP, they are both the radii of this quarter circle, and therefore they are equal to each other. And you know that AB equals to 1, therefore AP must be also equal to 1, because the radius of this quarter circle equals to 1 unit in its length. So AP also equals to 1. In the next step, we'll join points P and B together by a straight line. By joining points P and B, we created the right triangle, triangle PAB. So I'll copy the right triangle PAB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle PAB. I will remind to you that this angle equals to 90 degrees, angle PAB equals to 90 degrees, and also angle QCB, this angle also equals to 90 degrees, because of the fact that those two shapes are quarter circles. Okay. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle PAB that I copied from the original drawing. PA equals to 1 and AB also equals to 1. PA and AB, they are both the radii of this small quarter circle. So in this right triangle, PAB, according to the Pythagoras theorem, PB squared, that is the square of the hypotenuse, equals to PA squared plus AB squared. PB squared, that is the square of the hypotenuse, equals to PA squared. PA is 1, therefore PA squared is 1 squared, that is 1, plus plus AB squared. AB equals to 1 unit in its length, therefore AB squared is 1 squared, that is also 1. So in total, PB squared equals to 1 plus 1, that is 2. PB squared equals to 2. We take a root out of this equation, and finally we get that PB equals to the square root of 2 units. So the hypotenuse PB equals to the square root of 2 units in its length. The right triangle, triangle PAB, is also an isosceles triangle. Why? Because PA equals to AB. And we know that we focus on the right triangle, triangle PAB. On the right triangle, triangle PAB, we have P8 is equals to AB, and we have the rule that in front of equal sides in a triangle there are equal angles. So those two angles that are located in front, the equal sides, must be equal to each other. So if we define the size of this angle as alpha, then the size of the other angle must be also equal to alpha. In the right triangle, triangle PAB, the sum of the angles must be equal to 180 degrees. It is true in any triangle, and especially in the right triangle, triangle PAB. So which angles we have inside the right triangle PAB? We have angle alpha plus alpha, that is 2 alpha, plus this angle is equal to 90 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. Repeat again. The right triangle PAB, the sum of the angles is equal to 180 degrees. 2 alpha plus 90 degrees equals to 180 degrees. We subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So we found out that this angle alpha equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees in its size. In the big quarter circle, BC and QC, they are both the radii of this quarter circle, therefore they are equal to each other. But it is given as the question that BC equals to x, therefore QC must be also equal to x. So here, if we repeat on the same process, exactly like we did in the this small quarter circle, here we join points Q and B together by a straight line. By joining points Q and B, we created the right triangle, triangle QCB. So, if we repeat on the same process that we did in the small right triangle PAB, in the big right triangle QCB, we will find out that those two angles, they are both also equals to 45 degrees in their sizes. So I'll not repeat on the same process. We know that those two sides are equal to each other, and in front of equal sides in the triangle there are equal angles, so those two angles that are located in front the equal sides must be equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha. And the sum of the angles in the right angle QCB equals to 180 degrees. So alpha plus 90 degrees equals to 180 degrees. So 2 alpha plus 90 degrees equals to 180 degrees. We subtract 90 degrees from the equation, and we get that 2 alpha equals to 180 degrees plus 90 degrees, that is 90 degrees, so 2 alpha equals to 90 degrees. We divide the equation by 2, and finally we found out that alpha equals to 90 degrees over 2, that is 45 degrees. So those two angles, each of them is equal to 45 degrees in its size. Okay. In the next step, I will copy the right triangle QCB in a new page, and we'll implement the Pythagoras theorem on this right triangle QCB. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QCB that I copied from the original drawing. In this right triangle QCB, according to the Pythagoras theorem, QB squared equals to QC squared plus BC squared. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So QB squared, that is the square of the hypotenuse, in the right triangle QCB, will be equal to QC squared. QC is x, therefore QC squared is x squared plus BC squared. BC is x, therefore BC squared is x squared. So in total, QB squared equals to x squared plus x squared, that is 2x squared. Again, QB squared equals to 2x squared. We take a root out of this equation, and finally we get that QB equals to the square root of 2 times x squared. That is to say, QB equals to the square root of 2, and the square root of x squared is x. So in total, QB equals to the square root of 2 times x. So you can find down in the original drawing that the length of the hypotenuse in the QB in the right triangle QCB is equals to the square root of 2 times x units. Okay. In the next step, I present to you a new rule number 3, and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q. Here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule number 3. You can implement rule number 3 in our drawing. Why? Because in our drawing you have the straight line AC. So if we focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I'll copy the straight line AC with point B and with its angles, and we will implement rule number 3 in this straight line AC. So actually, this is the straight line AC that I copied from the original drawing. So at the upper side of the straight line AC at point B, the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees plus the missing angle that we define as x plus this angle that is also equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees plus the missing angle x. In total, the sum of those three angles must be equal to 180 degrees. We subtract 90 degrees from this equation and finally we get that the missing angle x equals to 180 degrees minus 90 degrees, it is 90 degrees. So we found out that this missing angle equals to 90 degrees in its size, that is to say it is a right angle. So we can write down that angle PBQ, that is the missing angle, is a right angle. And because of the fact that angle PBQ is a right angle, it means that triangle PBQ is a right angle. So I will copy the right angle triangle PBQ in a new page, and we will block this right angle triangle PBQ by a circle. We know that any triangle can be blocked by a circle, and especially this right triangle triangle PBQ. So I blocked this right triangle PBQ that I copied from the original drawing by this circle. So in the drawing we have peripheral PBQ. This peripheral PBQ equals to 90 degrees in its size. And we have rule number 5 that relates to any peripheral angle that is equals to 90 degrees. So I write it down. Peripheral angle PBQ equals to 90 degrees in its size. Again, peripheral angle PBQ, this peripheral angle PBQ equals to 90 degrees in its size. And we have rule number 5 that relates to a peripheral angle that is equals to 90 degrees. According to this rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So in the drawing we have a circle. Inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size. Therefore, according to this rule number 5, peripheral angle MAN rests on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle MAN rests on chord MN, this chord called MN, and therefore chord MN must be the diameter of the circle. And indeed, chord MN is the diameter of the circle. Why? Because chord MN passes through point O, that is the center of the circle. And you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord MN is the diameter of the circle. So in conclusion, according to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Okay, in this case, MN is the diameter of the circle. So we can actually implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle PBQ that is equal to 90 degrees in its size. Therefore, according to rule number 5, this peripheral angle PBQ rests on the diameter of the circle. From the drawing it is very easy to see that peripheral angle PBQ rests on chord PQ. Therefore, chord PQ is the diameter of the circle. So PQ is the diameter of this circle. According to rule number 5, of course. So if we define the radius of this circle as R, then the diameter PQ must be equal to 2R. For one side, PQ equals to 2R, it is the diameter of the circle, but from the other side, PQ in the drawing line segment PQ, we know that it is given us the equation that PS equals to SQ. So if we define PS as X, then SQ must be also equal to X because they are equal to each other. So in total, line segment PQ equals to PS plus SQ. That is to say, PQ equals to PS, that is X, plus SQ, that is X. So in total, PQ equals to 2X. So from the other side, PQ equals to 2X. And from those two equations, PQ equals to 2R and PQ equals to 2X, we will derive that two R equals to 2X. We will divide this equation by 2, and finally we get that R equals to X. Okay, R equals to X. So the radius of this circle equals to X. So here we can write down that X equals to R, and here also X equals to R. So here we have, so we copy points S to this drawing. Again, I copied this point S, from the original drawing to our drawing here. And PS equals to X. PS equals to X and X equals to R. So PS equals to R, SQ equals to X, and X equals to R. So SQ also equals to R. So QS equals to R and PS equals to R. So at point S, the two radii touch each other. And because of the fact that at point S, those two radii touch each other, point S must be the center of the circle. So I write down S, point S is the center of the circle. Repeat again, because of the fact that those two radii touch each other at point S must be the center of the circle. In the next step, we will join points S and P together by a straight line. Point S is the center of the circle, point B is a point on the circle itself, therefore SB is also the radius of this circle that is equals to R. In conclusion, we found out that PS equals to SQ equals to SP, they are all the radii of this circle, therefore they are equal to each other. So here we join points S and B together by a straight line in the original drawing. SB is the radius of the circle, equal to R. So SB equals to SP equals to SQ, and especially here SB equals to SQ. Okay. In the next step, we will complete this big quarter circle to a circle. So I'll copy this quarter circle to a new page and we'll complete it to a circle. So this is the quarter circle that I copied from the original drawing, and I completed this quarter circle to a circle. I found out that SQ equals to SB. SQ so SQ equals to R, SB equals to R. This, they are both the radii of the previous circle, therefore they are equal to each other. In the next step, we join points Q and B together by a straight line. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and peripheral angle ACB is subtended on arc AB. Again, this peripheral angle ACB is subtended on arc AB. And we have another angle, the central angle AOB. This central angle AOB is also subtended on the same arc AB. And according to this rule number 13, because of the fact that those two angles, they are both subtended on the same arc AB, therefore the central angle must be twice as large of this peripheral angle that's subtended on arc AB. Okay, and because of the fact that peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc AB must be equal to 2 theta. It is twice as large as this peripheral angle. So because of the fact that the peripheral angle equals to theta, then the central angle that is subtended on the same arc AB must be equal to 2 theta. Okay? So we can actually implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle QSB. Peripheral angle QSB. This is peripheral angle QSB. This peripheral angle QSB is subtended on arc BQ. Again, peripheral angle QSB is subtended on arc BQ. And we also have the central angle BCQ. This is the central angle BCQ. Again, this is the central angle BCQ that is subtended on the same arc BQ. And therefore, according to rule number 13, because of the fact that this peripheral angle and this central angle, they are both subtended on the same arc BQ, the central angle, must be twice as large of this peripheral angle. So, in order to find out what is the size of this central angle BCQ, I will present to you a new rule number 6, and we will implement rule number 6 in our drawing. Again, this is the central angle BCQ. Okay, you can see it, that it is more than 180 degrees. Okay, so we have rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around this point A, in total it must be equal to 360 degrees. In order to prove that this rule number 6 is true, I actually draw this straight line that passes through point A. Again, this straight line passes through point A. Or point A is located on this straight line. So here we can implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees. Again, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees from one side, but from the other side, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A plus the sum of the angles in the lower side of this straight line at point A, in total the sum of those two angles must be equal to 180 degrees plus 180 degrees, that is 360 degrees. Exactly according to this rule number 6, that states that the sum of the angles around point A is equal to 360 degrees. Okay, so we can actually implement rule number 6 in our drawing. Why? Because in our drawing, if we focus on this point, at this point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is equal to 90 degrees, plus the missing angle. This is the missing angle. In total, it must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus this angle that is 90 degrees, in total it is equal to 360 degrees, exactly like rule number 6. Therefore, this missing angle must be equal to 270 degrees in its size. And because of the fact that this central angle BCQ equals to 270 degrees in its size, the peripheral angle BSQ that is subtended on the same arc BQ must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. According to rule number 13. Here, the peripheral angle is half of the size of the central angle that is subtended on the same chord called BQ. Exactly according to rule number 13. So, we'll focus on the isosceles triangle, triangle BSQ. Why triangle BSQ is an isosceles triangle? Because of the fact that in triangle BSQ, side BS equals to side SQ. So in the isosceles triangle, triangle BSQ, the sum of the angles must be equal to 180 degrees. But before that, we have the rule that in front of equal sides in the triangle there are equal angles. So we have those two sides are equal to each other. Therefore, in front of those two sides, we have those two angles that must be also equal to each other. So if this is angle alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. Now we know that the sum of the angles in any triangle, and especially in the isosceles triangle, triangle BSQ, must be equal to 180 degrees. Okay, so which angles we have inside the isosceles triangle, triangle BSQ? We have alpha plus 135 degrees. In total, it must be equal to 180 degrees. So in the isosceles triangle, triangle BSQ, the sum of the angles must be equal to 180 degrees. That is to say, 2 alpha plus 145 degrees. In total, they must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. So alpha equals to 45 degrees. We divide this equation by 2, and finally we get that alpha equals to 45 over 2 degrees. So this is angle alpha that equals to 45 over 2 degrees, and this is also angle alpha that is equals to 45 over 2 degrees. So angle SQB equals to 45 over 2 degrees in its size. So here we have angle SQB. This is angle SQB. That is equals to 45 over 2 degrees. This is angle alpha. In the next step, I will copy the right triangle, triangle PBQ, in a new page, and we'll analyze this right triangle, triangle PBQ. Side PB of the right triangle PBQ equals to the square root of 2 units in its length. This is side QB of the right triangle PBQ, that is equals to square root of 2 times x units in its length. and this is actually angle PQB, that's equal to 45 over 2 degrees. So actually, this is the right triangle PBQ that I copied from the original drawing. In this right triangle PBQ, tangents 45 over 2 degrees will be equal to PB over BQ. Again, tangents 45 over 2 degrees equals to PB over BQ. So I write it down. Tangents 45 over 2 degrees equals to PB over BQ. PB equals to the square root of 2 units in its length over BQ. BQ equals to the square root of 2 times x units in its length. So we have here square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled, and we left this expression equals to 1 over x. In conclusion, I found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. So I write it down. According to equation number 1, I found out that tangents 45 over 2 degrees is equals to 1 over x. This is according to equation number 1. But we also have the trigonometric identity according to the following trigonometric identity: tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. Again, tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. In the next step, we define theta as 45 over 2 degrees. So if theta is 45 over 2 degrees, then 2 theta must be 45 degrees. And we'll substitute theta in this trigonometric identity by 45 over 2 degrees, and we'll substitute 2 theta by 45 degrees in this trigonometric identity. This will be equation number 2, and we'll get that tangents 2 theta is 45 degrees, is equals to 2 tangents theta. And theta, according to our definition, is 45 over 2 degrees, all divided by 1 minus tangents square theta. and theta, according to our definition, is 45 over 2 degrees. So if we already found out that according to equation number 2 times 45 degrees equals to 2 times 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. So here tangent 45 degrees is 1, and it is equals to 2 tangent 45 over 2 degrees. We define tangent 45 over 2 degrees as t. Repeat again. According to our definition, tangent 45 over 2 degrees equals to t, and therefore we substitute tangent 45 over 2 degrees in this equation number 2 by t. So it will be 2 times tangent 45 degrees over 2 is t. So in total, in the numerator we will have 2t, because this is t. Again, in the numerator of equation number 2, we have 2t over 1 minus tangent square 45 over 2 degrees. According to our definition, tangent 45 over 2 degrees is t, therefore tangent square 45 over 2 degrees must be t square. So in the numerator we have here in total 1 plus t square. So in conclusion, we found out that according to equation number 2, one equals to 2t over 1 plus t square. Here we will multiply this equation number 2 by 1 minus t square, and we get that according to this equation number 2, 1 minus t square equals to 2t. Here we will add t square to this equation number 2, and we get that according to equation number 2, this equation number 2, 1 equals to t square plus 2t. Here we subtract 1 from this equation number 2, and finally we get that according to equation number 2, t square plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. Here. Now we can put the data of our specific quadratic equation in order to find out the value of the values of t, because in our specific quadratic equation x equals to t. We do it now and we get that x is t, so t equals to minus b. b is 2, therefore minus b is minus 2, plus minus square root of b squared. b is 2, so b squared is 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 1. All divided by 2 times a. a is 1, so it is 2 times 1. So in conclusion, we found out that t equals to minus 2 plus minus square root. Inside the root we have 4, and minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8. Over 2 times 1 is 2. In conclusion, we found out that the solution to our specific quadratic equation, the variable that we are looking for is t, and t equals to minus 2 plus minus square root of 8 over 2. So t equals to minus 2 plus minus square root of 8. 8 is 4 times 2, so substitute 8 by 4 times 2, all divided by 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we have to leave with 2. All divided by 2. So t equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1, so in total this expression equals to square root of 2. In conclusion, we found out that t equals to minus 1 plus minus square root of 2. So here we will have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2, and the second solution that is possible for t is that t equals to minus 1 plus square root of 2. So according to the first solution, t equals to minus 1 minus square root of 2, that is a negative number. So according to the first solution, t is a negative number. T is a negative number because it is equals to minus 1 minus square root of 2, that is a negative number. But according to our definition, t equals to tangents 45 over 2 degrees. That is a positive number. T is a positive number. T cannot be simultaneously a negative number and a positive number. A negative number can never be equal to a positive number. So we have a contradiction. We cancel the solution, and we have to live with the second solution that is possible for t. That is to say t equals to minus 1 plus square root of 2. Again, according to our definition, t equals to tangents 45 over 2 degrees. So tangents 45 over 2 degrees is t, and t equals to, according to the second solution, t equals to minus 1 plus square root of 2. So in conclusion, according to equation number 2, we found out that tangents 45 over 2 degrees equals to minus 1 plus square root of 2. This is according to equation number 2. While according to equation number 1, we have already found out that t equals to 1 over x. Here, according to equation number 1, we have already found out that tangents 45 degrees over 2 equals to 1 over x. Again, according to equation number 1, we found out that tangents 45 over 2 degrees equals to 1 over x. So I copy this equation number 1 in our here. According to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. So here we have two equations for tangents 45 over 2 degrees. Therefore, we get equation number 3 that states that tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Repeat again on equation number 3. According to equation number 3, tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 degrees over tangents 45 over 2 degrees according to equation number 2. Tangents 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to tangents 45 over 2 degrees according to equation number 2, that is minus 1 plus square root of 2. In conclusion, we found out that according to equation number 3, 1 over x equals to minus 2 plus square root of 2. Okay. So here we'll multiply this equation number 3 by x, and we get that according to this equation number 3, 1 equals to minus 1 plus square root of 2 times x. Here we will divide this equation number 3 by minus 1 plus 2, minus 1 plus square root of 2. And we get that according to this equation number 3, x equals to 1 over minus 1 plus square root of 2, or according to equation number 3, actually found out that x equals to 1 over square root of 2 minus 1. Okay. I found out the value of x. That is the value that we are looking for. We want to know that our mission is to find out the length of line segment BC is equal to x. We have to find out the value of x, or the length of line segment x. And found out that x equals to 1 over square root of 2 minus 1. Here we will multiply, so x, according to equation number 3, equals to 1 over square root of 2 minus 1. Now we will multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. So we actually multiplied x by 1, so we change nothing, therefore this operation is allowable. Again, square root of 2 plus 1 over square root of 2 plus 1 is 1. It is allowable to multiply anything by 1. Okay, so we found out actually that x equals to, in the numerator we have square root of 2 plus 1 over, in the numerator we have square root of 2 minus 1 times square root of 2 plus 1. And we have the algebraic identity that a minus b times a plus b equals to a square minus b square. Again, a minus b times a plus b equals to a square minus b square. According to this trigonometric identity, the value of the expression square root of 2 minus 1 times square root of 2 plus 1 will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in conclusion, we found out that x equals to the square root of 2 plus 1 over 2 minus 1 is 1. So anything that is divided by 1 doesn't change the value of the expression. So square root of 2 plus 1 over 1 is square root of 2 plus 1. So I actually found out that x equals to the square root of 2 plus 1 units in terms of numbers. X equals to 2.414 units. Repeat again. The length of line segment BC is equal to x is equals to either square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. This is a little bit less than 2.5 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment BC, is equal to x. So in the drawing, we have those two quarter circles. The two quarter circles start each other here at point B. In addition, we know that the length of line segment AB is equals to 1 unit. We also know that line segment QS equals to line segment SP, and our mission is to find out the length of this line segment BC that is equal to x. Okay. So this is a quarter circle, and therefore in any quarter circle, this angle is the right angle is equal to 90 degrees, and we also know that PA and AB, they are the radii of this quarter circle, therefore they are equal to each other. But AB equals to 1, therefore PA must be also equal to 1. Okay, then we join points P and B together by a straight line. By joining points P and B, we created the right triangle PAB. So I copied the right triangle PAB in a new page, and we implemented the Pythagoras theorem on this right triangle PAB. Actually, this is the right triangle PAB that I copied from the original drawing. In this right triangle PAB, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1 square, that is also 1. So in total, PB square equals to 1 plus 1, that is 2. So PB square equals to 2. We took out of this equation, and finally found out that PB equals to the square root of 2 units. So the hypotenuse PB equals to the square root of 2 units. So we can write down in the original drawing that the length of the hypotenuse PB is square root of 2 units. Then we focused on this right triangle PAB. In this right triangle, the right triangle PAB is also an isosceles triangle. Why? Because PA equals to AB. PA equals to AB. So, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, and then the other angle must be also equal to alpha because they are equal to each other. So, and we also know that the sum of the angles in any triangle, and especially in the right triangle PAB, must be equal to 180 degrees. So which angles we have in the right triangle PAB? We have angle alpha plus angle alpha plus 90 degrees. In total, it must be equal to 180 degrees. I'll repeat again. In the right, in the isosceles triangle PAB, alpha plus alpha is 2 alpha, so 2 alpha plus 90 degrees must be equal to 180 degrees. Here we subtracted 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees in its size. Okay, then we join points Q and B together by a straight line. In this big quarter circle, QC and CB, they are both the radii of this quarter circle, therefore they are equal to each other. According to what is given us in the equation, BC equals to x. X is the thing that we want to find the length of x. Our mission is to find out the length of Right 7 BC is equal to x. So we know that BC equals to x, therefore QC must be also equal to x. Because of the fact that those two sides are both the radii of this quarter circle, therefore they are equal to each other. Then I copied the right triangle QCB in a new page and implemented the Pythagoras theorem in this right triangle QCB. Actually, this is the right triangle QCB that I copied from the original drawing. In this right triangle QCB, QB square equals to QC square plus BC square. So QB square, that is the square of the hypotenuse, in this right triangle QBC, equals to QC square. QC is x, therefore QC square is x square, plus BC square. BC is x, therefore BC square is also x square. So in total, QB square equals to x square plus x square, that is 2x square. QB square equals to 2x square. We took out all of this equation, and finally found out that QB equals to the square root of 2 times x square. That is to say, QB equals to the square root of 2, and the square root of x square is x. So in total, QB equals to the square root of 2 times x units. Here, therefore, QB of the right triangle QBC equals to the square root of 2 times x units. Okay. Then I presented to you rule number 3 and we implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q here, the sum of the angles must be equal to 180 degrees. So which angles we have the upper side of AB at point Q, we have this angle alpha and beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. Actually, you can implement rule number 3 in our drawing. In our drawing, if we focus on the straight line, on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC with point B with its angles in a new page, and we implemented rule number 3 on this straight line AC. This is the straight line AC that I got from the original drawing. This is point B. So here we know that the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees, plus this missing angle that we defined as angle x, plus this angle is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So in total, in this side of the equation, we have 90 degrees plus x that is equal to 180 degrees. Here we subtracted 90 degrees from this equation, and finally found out that x equals to 180 degrees minus 90 degrees, it is 90 degrees. So the missing angle here, x equals to 90 degrees in its size. So we can write down in the original drawing that this is the missing angle PBQ. It is a right angle, it is equal to 90 degrees in its size. Then I copied the right triangle PBQ. So if this angle equals to 90 degrees, it means the triangle PBQ is a right angle. So I copied the right triangle PBQ in a new page, and we blocked this right triangle PBQ by a circle. You know that any triangle can be blocked by a circle. So actually, this is the right triangle PBQ that I copied from the original drawing, and I blocked this right triangle PBQ by this circle. So in the drawing we have here a circle. Inside this circle we have peripheral angle PBQ that is equal to 90 degrees in its size. And we have rule number 5 that relates to any peripheral angle that is equal to 90 degrees. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So in the domain we have a circle. Inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size. Therefore, according to this rule number 5, peripheral angle MAN rests on the diameter of the circle. Indeed, it is very easy to see that peripheral angle MAN rests on chord MN. And chord MN is indeed the diameter of the circle. Why? Because chord MN passes through point O, that is the center of the circle. And you know that any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN equals to 90 degrees, it rests on the diameter of the circle. Here MN is the diameter of the circle. We can implement rule number 5 in our drawing. Why? Because in our drawing we have this peripheral angle PBQ that is equal to 90 degrees in size. Therefore, according to rule number 5, this peripheral angle PBQ rests on the diameter of the circle. That is to say, PQ is the diameter of the circle. According to rule number 5, PQ is the diameter of the circle. So if you define the radius of this circle as R, then the diameter PQ must be equal to 2R. From one side, the diameter PQ equals to 2R. This is the diameter of the circle. But from the other side, PQ, this is PQ, and it is given as a equation that PS equals to SQ. Again, PS equals to SQ, so if PS is X, then SQ must be also equal to X, because they are equal to each other. So in total, PQ equals to PS, that is X, plus SQ, that is also X. So in total, PQ equals to X plus X, that is 2X. So from the other side, PQ equals to 2X. Yet from the other side, PQ equals to 2X. So PQ equals to 2R, this is the diameter of the circle, and PQ equals to 2X. So from those two equations, we derive that 2R equals to 2X. We divide this equation by 2 and finally found out that R equals to X. Okay, so here R equals to X. PS that is equals to X equals to R, and SQ that is equal to X equals to R. Then I copied point S from the original drawing to our drawing here. Copied point S to our drawing here. So we found out that PS equals to X and X equals to R, and SQ equals to X and X equals to R. Okay, so PS equals to R and SQ equals to R. And at point S, the two radii touch each other. And because of the fact that at point S the two radii touch each other, it means that point S is the center of this circle. Okay, point S is the center of the circle. Then we join points S and B together by straight line. Point S is the point in the center of the circle, point B is the point of the circle itself, therefore SB is the radius of this circle that is equal to R. So in conclusion, we found out that PS equals to SQ equals to SB. They are all the radii of this circle, therefore they are equal to each other. So here we join points S and B. SB is the radius of the previous circle that is equal to R. SQ also equals to R, and SP also equals to R. So those three line segments are both equal to each other. And especially QS equals to SB. Okay. Then I copied this quarter circle to a new page, and we completed this quarter circle to a circle. So actually, this is the quarter circle that I got from the original drawing. I completed this quarter circle to a circle. we have already found out that QS equals to SB. Here, QS equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. Then I join points Q and B together by a straight line. And then I presented to you a new rule and we implemented the new rule in our drawing. According to the new rule, rule number 13, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle, inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and peripheral angle ACB is subtended on this arc RKB. In addition, in this drawing we have central angle AOB. This central angle AOB is also subtended on the same arc RKB. So because of the fact that those two angles subtended on the same arc, therefore the central angle AOB must be twice as large as the peripheral angle ACB that is subtended on the same arc. So if the peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc RKB must be equal to 2 theta. We can actually implement rule number 13 in our drawing. Why? Because in our drawing we have peripheral angle BSQ. This peripheral angle BSQ is subtended on arc BQ. And we also have central angle BCQ. This is the central angle BCQ. This central angle BCQ is subtended on the same arc BQ. And therefore the central angle must be twice as large of the peripheral angle BSQ that is subtended on the same arc BQ. So we have to find out the size of the central angle BCQ. We find out according to rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have point A. According to this rule, rule number 6, the sum of the angles around point A must be equal to 360 degrees in total. In order to prove that rule number 6 is true, I drew this straight line that passes for point A. And here we have rule number 3. According to rule number 3, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees from one side. But from the other side, according to the same rule, rule number 3, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A plus the sum of the angles in the lower side of this straight line at point A will be equal to 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule, rule number 6, that says that the sum of the angles around point A must be equal to 360 degrees. We can actually implement rule number 6 in our drawing. Why? Because in our drawing, if you focus at this point, point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So we have around point C, we have this angle that is equal to 90 degrees, plus this missing angle, in total they must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees is equal to 360 degrees. That is the sum of the angles around any point, and especially around point C, according to rule number 6. So this missing angle equals to 270 degrees in its size. That is to say, the center angle BCQ equals to 270 degrees in size. Therefore, according to rule number 13, the side of this angle BSQ that is subtended on the same arc RBQ must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So then we focused on the associated triangle BSQ. In the associated triangle BSQ, side BS equals to side SQ. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we have the rule that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle in the associated triangle BSQ. So which angles we have inside the associated triangle BSQ? We have this angle alpha plus alpha, that is 2 alpha, plus 135 degrees. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So, in the associated triangle BSQ, 2 alpha plus 135 degrees must be equal to 180 degrees. Here we subtracted 135 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees. 145 degrees is 45 degrees. So 2 alpha equals to 45 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 degrees, 45 over 2 degrees. So this is angle alpha that is equal to 45 over 2 degrees. This is also angle alpha that is equal to 45 over 2 degrees. Okay. Then I copied the right triangle PBQ in a new page, and we analyze this right triangle PBQ. This is the right triangle PBQ that I copied from the original drawing. Side PB equals to the square root of 2 units in itself. Side BQ equals to the square root of 2 times x units in itself. And this is angle alpha that is equal to 45 over 2 degrees. And this is angle alpha that is equal to 45 over 2 degrees. So this right triangle PBQ times 45 over 2 degrees equals to PB over BQ. Again, times 45 over 2 degrees equals to PB over BQ. PB is square root of 2 and BQ is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 we get cancelled and we left only with 1 over x. So in conclusion, found out that according to this equation number 1, times 45 over 2 degrees equals to 1 over x. Okay, times 45 over 2 degrees equals to 1 over x. This is according to equation number 1, but we have also the trigonometric identity that states that times 2 alpha equals to 2 times alpha over 1 minus tangent square, again times 2 theta equals to 2 tangent theta over 1 minus square theta. Then we defined theta is 45 over 2 degrees. If theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. And we substitute theta in this trigonometric identity by 45 over 2 degrees. We substitute 2 theta by 45 degrees. And I found out that according to this trigonometric identity, tangents 2 theta is 45 degrees, equals to 2 times tangents theta. And theta is 45 over 2 degrees over 1 minus tangent square theta. And theta is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, times 45 degrees equals to 2 times tangent 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. So tangent 45 degrees is 1, and we defined tangent 45 over 2 degrees as t, and we substitute tangent 45 over 2 degrees by t. Okay, again, we define sinus 45 over 2 degrees as t, and we substitute sinus 45 over 2 degrees in equation number 2 by t. We found out sinus 45 degrees is 1, and it is equal to 2 times sinus 45 over 2 degrees, so sinus 45 over 2 degrees is t. So in the numerator we have 2t over 1 minus sinus square 45 over 2 degrees. So if sinus 45 over 2 degrees is t, then sinus square 45 over 2 degrees will be equal to t square. So in total, the denominator we have 1 minus t square. Here we multiply this equation number 2, by 1 minus t square, and found out that according to equation number 2, 1 minus t square equals to 2t. Then we added t square to this equation number 2, and finally found out that 1 equals to t square plus 2t. We subtracted 1 from this equation number 2, and finally found out that t square plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. We'll find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for is t, so x equals to t. The coefficient a is 1, the coefficient b is 2, and the coefficient c is minus 1. So we now have to put the data that we have for our specific quadratic equation inside this general formula in order to find out the values of t, because in our specific quadratic equation the variable that we are looking for is t. So x equals to t, so we substitute x by t. So t equals to minus b, b is 2, so minus b is minus 2, plus minus square root of b squared, b is 2, so b squared is 2 squared, that is 4, minus 4 times a is 1, times c is minus 1, over 2a. A is 1, so 2a is 2 times 1. So actually found out that here inside the root we have 4 minus 4 times minus 1 is 4. So in total, inside the root we have 4 plus 4, that is 8. So in conclusion, we found out that t equals to minus 2 plus minus, inside the root we left only with 8 over 2. So t equals to minus 2 plus minus 8 is 4 times 2 over 2. So t equals to minus 2 plus minus the square root of 4 is 2, and inside the root we left only with 2. So in total we found out that t equals to minus 2 plus minus 2 times square root of 2 over 2. Minus 2 over 2 is minus 1, and 2 over 2 is 1. So in total this expression equals to square root of 2. So in conclusion, found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is the solution to our quadratic equation. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t is that t equals to minus 1 plus square root of 2. According to the first solution, t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2 is a negative number, so t is a negative number. But according to our definition, t equals to minus 45 over 2 degrees, that is a positive number. A positive number can never be equal to a negative number. So cancel the solution, we left only the second solution that is possible for t, that t equals to minus 1 plus square root of 2. Again, according to our definition, t equals to also to minus 45 over 2 degrees. So we can write down here that t that is times 45 over 2 degrees equals to t that is minus 1 plus square root of 2. This is according to equation number 2, while according to equation number 1, we have already found out that times 45 over 2 degrees equals to 1 over x. So we have two different equations for times 45 over 2 degrees. Therefore, we created equation number 3 that states that times 45 over 2 degrees according to equation number 1 must be equal to times 45 over 2 degrees according to equation number 2. Times 45 over 2 degrees according to equation number 1 is 1 over x. And it must be equal to times 45 over 2 degrees according to equation number 2, that is minus 1 plus root of 2. So in conclusion, found out that according to equation number 3, 1 over x equals to minus 1 plus root of 2. Here we multiply this equation number 3 by x, and found out that 1 equals to minus 1 plus root of 2 times x. Here we divided this equation number 3 by minus 1 plus root of 2, and finally found out that x equals to 1 over minus 1 plus root of 2. Again, according to equation number 3, we found out that x equals to 1 over square root of 2 minus 1. We just change the order of the two expressions. A plus b is b plus a. Okay, so x equals to 1 over square root of 2 minus 1, according to this equation number 3. And that is the answer to our question. And here we focus on this side of the equation number 3, and we multiplied this side by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1, so we change nothing. So in conclusion, found out that x equals to, in the numerator we have square root of 2 plus 1, in the denominator we have square root of 2 minus 1 times square root of 2 plus 1. This expression equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. We find out that this expression equals to the square root of 2 square, that is 2, minus the square root of 1 square, that is 1. So in total, in this expression equals to 2 minus 1, that is 1. So in conclusion, found out that x equals to the square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. Repeat again, the length of this line segment BC is equal to x, is equals to either square root of 2 plus 1 units, or in terms of numbers, BC is equal to x equals to 2.414 units. Okay, thank you very much.